Right now, at this very moment, something enormous is racing toward us. Not a comet, not an asteroid, not some rogue planet flung from its orbit. Something far, far bigger, something containing roughly 1 trillion stars. A supermassive black hole with 100 million times the mass of our sun. And enough mass and gravitational pull to reshape the entire future of our galaxy. It is 2.5 million light years away, and it is closing the distance between us at roughly 250,000 miles per hour. That is fast enough to travel from the Earth to the Moon in about an hour, and it has been coming for us for billions of years. Its name is the Andromeda Galaxy, and when you step outside on a clear autumn night, far from the glow of city lights, you can actually see it with your own eyes. That faint, hazy smudge of light, no bigger than the width of the moon, is the most distant thing a human being can perceive without any instrument at all. It looks impossibly small. It looks utterly harmless. It looks like nothing more than a tiny imperfection in the fabric of the night sky. But that faint smudge is a colossus. It is a spiral galaxy wider than 150,000 light years across. It contains more stars than you could count if you spent every second of every day counting, 1 per second, for over 30,000 years. And it is not sitting still. It is falling toward us, pulled by the combined gravity of itself and our own Milky Way. 2 cosmic heavyweights locked in a gravitational embrace that has been tightening since both galaxies were young for over a century. Astronomers assumed the collision between these 2 titans was inevitable. A head-on galactic crash, billions of years in the future, that would reshape both galaxies entirely, but in a twist that has shaken the astronomical community. A groundbreaking study published in 2025 threw that certainty into question. After running 100,000 computer simulations using the most precise data ever gathered, scientists found that the odds of Andromeda and the Milky Way actually colliding may be closer to a coin flip than anyone previously believed. The collision that was once considered a certainty may never happen at all. So, what is Andromeda, really? How did we discover it? What do we actually know about this colossal neighbor of ours? And what would happen to us, to our sun, to our solar system, if these 2 galaxies really do collide? This is the story of the Andromeda Galaxy. And it begins, like so many great stories in science, with someone looking up at the sky and noticing something strange. Let's take a moment to appreciate the sheer absurdity of scale here, because the numbers involved are so large that they stop feeling real very quickly. The distance between Andromeda and us, 2.5 million light years, means that the light reaching your eyes from that faint smudge in the sky tonight left the Andromeda Galaxy 2.5 million years ago. When those photons began their journey toward Earth, our ancestors were barely beginning to fashion the first stone tools. Homo habilis was walking the African savanna. The entire saga of human civilization, from the first cities of Mesopotamia to the launch of the James Webb Space Telescope, unfolded in the time it took that light to cross the gulf of space between us. And yet, on the cosmic scale, Andromeda is close. It is our next-door neighbor, the nearest large galaxy to our own. If you imagine the Milky Way as a house on a suburban street, Andromeda would be the house next door, and these two houses are slowly sliding toward each other. Over 1,000 years ago, in a city called Isfahan, in what is now modern-day Iran, a Persian astronomer named Abd al-Rahman al-Sufi was doing something that would change the course of human understanding forever. He was writing a book. Not just any book, but a meticulous catalog of every star and celestial object visible in the night sky. A work he called the Book of Fixed Stars. It was roughly the year 964. And al-Sufi was working under the patronage of the Buyid ruler Adud al-Dawla, refining and expanding upon the ancient star catalogue of the Greek astronomer Ptolemy, whose Almagest had been the definitive guide to the heavens for nearly 800 years. Al-Sufi was thorough. He listed over 1,000 stars, their positions, their estimated brightnesses, and their colors. He drew illustrations of the constellations, blending the Greek traditions with the Arabic star lore that had developed independently over centuries. Many of the star names we still use today, names like Aldebaran, Betelgeuse, Rigel, and Vega, trace their origins directly to al-Sufi's catalog. He was, by any measure, one of the greatest observational astronomers of the medieval world, and buried within his notes on the constellation of Andromeda, he wrote something remarkable. He described a nebulous smear, or a little cloud, sitting near the mouth of a large fish, an Arabic constellation that overlapped with the Greek figure of the chained princess. It was small, it was faint, it was easy to miss, and no Greek astronomer, not even Ptolemy himself, had ever mentioned it. That little cloud was the Andromeda Galaxy, and al-Sufi's observation was the first recorded reference to any galaxy beyond our own Milky Way. More than 1,000 years before we understood what galaxies even were, a Persian nobleman in Isfahan had looked up, noticed something others had overlooked, and written it down. For centuries after al-Sufi, the little cloud remained just that, a curiosity. In 1612, the German astronomer Simon Marius became one of the first Europeans to observe it through a telescope, describing the light as looking like a candle shining through a translucent horn. Charles Messier, the famous French comet hunter, catalogued it in 1764 as the 31st object in his list of things that were not comets, giving it the designation Messier 31 or M31, a name it carries to this day. Messier, somewhat ironically, credited Marius with the discovery, apparently unaware of al-Sufi's observation almost 7 centuries earlier. But nobody truly understood what this object was. Was it a cloud of gas and dust within our own Milky Way? Perhaps a region where new stars were forming? Was it some kind of unresolved cluster of faint stars? Or was it something else entirely? Something far more distant and far more extraordinary than anyone had imagined. The question simmered for over a century, and it eventually came to a boil in one of the most famous intellectual showdowns in the history of science. Throughout the 19th century, astronomers had discovered something remarkable about many of these mysterious nebulae. They were spirals. In 1845, the Irish astronomer William Parsons, the 3rd Earl of Ross, had built the largest telescope in the world, a behemoth with a 72-inch mirror that he installed on the grounds of his castle in central Ireland. Looking through this mighty instrument at a nebula in the constellation Canes Venatici, he was the first to discern spiral structure, curving arms of faint light pinwheeling outward from a central core. He sketched what he saw, and his drawings bear a striking resemblance to modern photographs of spiral galaxies. Other nebulae turned out to have spiral structures too, including the Andromeda Nebula. But what were they? By the turn of the 20th century, two fundamentally different views had developed. One camp believed the spiral nebulae were small, relatively nearby features within our own Milky Way, perhaps regions where new solar systems were forming. The other camp believed they were island universes, a term borrowed from the philosopher Immanuel Kant, who had speculated in 1755 that some nebulae might be entire galaxies comparable to our own, scattered throughout an incomprehensibly vast cosmos. The tension between these two views reached its climax on the evening of April 26, 1920. On the evening of April 26, 1920, two astronomers walked into the Baird Auditorium of the Smithsonian Museum of Natural History in Washington, D.C. One was Harlow Shapley, a rising star at the Mount Wilson Observatory in California, who had recently made groundbreaking measurements of the size of the Milky Way. The other was Heber Curtis, a senior astronomer at the Lick Observatory, who had spent years studying the so-called spiral nebulae, those mysterious pinwheel-shaped smudges scattered across the sky, of which Andromeda was the largest and most prominent. The event would become known as the Great Debate, and the question at its heart was simple but staggering in its implications. How big is the universe? Shapley argued that the Milky Way was enormous, roughly 300,000 light-years across, and that it constituted the entire universe. In his view, the spiral nebulae were nothing more than relatively nearby clouds of gas, inconsequential objects floating on the outskirts of our galaxy. The universe was big, sure, but it was essentially just one giant galaxy. Curtis took the opposite position. He believed the Milky Way was much smaller, and that the spiral nebulae were in fact island universes, entire galaxies in their own right, separated from us by vast gulfs of intergalactic space. He pointed to the dark lanes of dust visible within the Andromeda Nebula, which looked strikingly similar to the dust clouds in our own galaxy. He cited the observations of novae, exploding stars, that appeared much fainter in Andromeda than novae seen within the Milky Way, suggesting that Andromeda was extremely far away. And he highlighted the blue shift measurements that the astronomer Vesto Slipher had made at the Lowell Observatory in Arizona. Slipher's work had been genuinely pioneering, and it deserves more attention than it typically receives. Vesto Melvin Slipher was a quiet, meticulous man who spent virtually his entire career at the Lowell Observatory in Flagstaff, Arizona, an observatory founded by the wealthy astronomer Percival Lowell, who was obsessed with the idea that there might be canals on Mars. Slipher had been assigned to study the spiral nebulae using spectroscopy, a technique that involves splitting the light from an object into its component wavelengths, like passing sunlight through a prism. By examining the exact positions of spectral lines in the light, astronomers could determine whether an object was moving toward or away from us, and at what speed. Beginning in 1912, Slipher turned his spectrograph on the Andromeda Nebula. The observations were excruciatingly difficult. The nebula was faint, and gathering enough light to produce a usable spectrum required exposure times of many hours, sometimes stretching across multiple nights. Slipher had to carefully track the nebula with his telescope for the entire duration, a task that demanded extraordinary patience and skill. What he found was astonishing. The light from Andromeda was blue-shifted, meaning it was compressed toward shorter wavelengths, which could only mean one thing. The Andromeda Nebula was moving toward us at a velocity of about 300 kilometers per second. This was the highest radial velocity of any celestial object ever measured at the time. It was moving at a speed that would take it from Los Angeles to New York in about 13 seconds. Nothing in the solar system moves that fast. Slipher went on to measure the velocities of dozens of other spiral nebulae over the following years, finding that almost all of them were redshifted, meaning they were moving away from us, many at extraordinary speeds. His presentation of these results at the 1914 meeting of the American Astronomical Society earned him a rare standing ovation from his colleagues, a moment of genuine recognition for work that was painstaking, brilliant, and deeply important. But even Slipher didn't know what to make of his own data. Were these nebulae galaxies? Were they escaping our own galaxy? Were they being flung outward by some unknown force? He could measure speeds, but not distances. The spectral lines told him how fast these objects were moving, but they said nothing about how far away they were. The answer to that question would require an entirely different kind of observation and an entirely different kind of astronomer. The answer came 3 years after the Great Debate, and it came from a man whose name would become synonymous with the expansion of the universe. Edwin Powell Hubble was, by all accounts, a complicated person, tall, athletic, and charismatic. He had studied law at Oxford on a Rhodes Scholarship before abandoning the legal profession to pursue his true passion, astronomy. He arrived at the Mount Wilson Observatory in California in 1919, where he had access to the most powerful telescope in the world, the 100-inch Hooker reflector, a marvel of engineering perched on a mountaintop above Los Angeles. On the night of October 5, 1923, Hubble was sitting at the eyepiece of this enormous telescope. He was examining a photographic plate he had taken of the Andromeda Nebula, looking for novae, those brief stellar explosions that Curtis had used in his arguments. He found one, then he found another. And then, examining the plate more carefully, he realized something that made him scratch out the letter N. He had written next to one of the stars and replace it with a word that would reshape human understanding of the cosmos. He wrote VAR with an exclamation point. The star was not a nova at all. It was a Cepheid variable, a type of pulsating star whose brightness waxes and wanes in a regular, predictable rhythm. And here was the key. an insight made possible by the work of one of the most under-recognized scientists in history. Henrietta Swan Leavitt was a computer at the Harvard College Observatory, one of a group of women who were hired at low wages to catalog and analyze the positions and brightnesses of stars from photographic plates. Despite the modest title, the work required real scientific skill, and Leavitt had it in abundance. While studying Cepheid variable stars in the small Magellanic Cloud, she noticed something remarkable. There was a direct, predictable relationship between the period of a Cepheid's pulsation and its intrinsic brightness. A Cepheid that pulsed slowly was intrinsically brighter than one that pulsed quickly. This period luminosity relationship, published by Leavitt in 1912, was one of the most important discoveries in the history of astronomy. It turned Cepheid variables into cosmic yardsticks, if you know how bright a Cepheid actually is, because its period tells you, and you can measure how bright it appears from Earth. Then the difference between those two brightnesses gives you the distance. The dimmer the star appears relative to its intrinsic brightness, the farther away it is. Hubble recognized immediately what the Cepheid in Andromeda meant. He measured the star's period, applied Leavitt's relationship, and did the calculation. The Cepheid variable he had found in Andromeda, later designated Vone, was impossibly far away. It placed the Andromeda Nebula at a distance of roughly 900,000 light-years, well beyond the boundaries of even Shapley's inflated Milky Way. Later measurements would revise this distance upward to about 2.5 million light-years. But even Hubble's initial estimate was enough to settle the great debate decisively. Andromeda was not a cloud of gas within our galaxy. It was an entirely separate galaxy, a vast island of stars floating in the depths of intergalactic space. When Hubble communicated his findings to Shapley in a letter, the effect was devastating. Shapley reportedly handed the letter to a colleague, Cecilia Pangapishkin, who happened to be in his office at the time, and said with grim finality, "Here is the letter that destroyed my universe." The reaction was understandable. Shapley had spent years building his model of the cosmos, a model in which the Milky Way was everything and Andromeda was nothing. And now, in a single stroke, a pulsating star had demolished that entire framework. The universe was not one galaxy. It was countless galaxies, each one a vast city of stars, scattered across distances that defied human comprehension. And with that, the universe as humanity understood it expanded by a factor that is almost impossible to grasp. Overnight, the cosmos went from being a single galaxy to being an arena of countless galaxies, each containing billions of stars, stretching in every direction to distances that stagger the imagination. Andromeda was not just a smudge. It was a world as vast and complex as our own. Hubble didn't stop there. Using Slipher's velocity measurements alongside his own distance calculations, he went on to formulate one of the most profound discoveries in the history of science, that the universe is expanding, with galaxies flying apart from each other at speeds proportional to their distances. As Hubble himself wrote to Slipher, he was using your velocities and my distances. The law that describes this relationship still bears Hubble's name, though some have argued it should rightfully be called the Hubble-Leavitt-Slipher law, given how fundamentally it depended on the work of all three scientists. But before any of that was possible, it was a single flickering star in the Andromeda Galaxy that blew open the doors to a universe far grander than anyone had dared to imagine. It is worth pausing here to reflect on the magnitude of this shift in human understanding. Before Hubble's discovery, humans believed the entire universe was contained within a single galaxy, the Milky Way, and that beyond it, there was nothing at all. After Hubble's discovery, we realized that our galaxy was just one of what we now estimate to be over 2 trillion galaxies in the observable universe, each one containing millions or billions or even trillions of stars. The Andromeda Galaxy was the key that unlocked this understanding. Without it, without that one faint smudge in the northern sky being close enough and bright enough for us to study, we might have lived in our blissful ignorance for decades longer. So what exactly is this galaxy that changed everything? What does Andromeda actually look like up close? And what do we know about it today? The Andromeda Galaxy, catalogued as Messier 31, is a barred spiral galaxy located approximately 2.5 million light-years from Earth. It is the largest galaxy in the local group, the cluster of galaxies that includes our own Milky Way, and it is one of the most luminous galaxies in the observable universe. To the naked eye on a dark night, it appears as a faint, elongated glow, roughly 6 times the apparent width of the full moon. Though our eyes can only detect the brightest central region, if we could see the full extent of Andromeda with our unaided eyes, including its faint outer halo, it would appear strikingly large in the sky, a testament to just how close this enormous galaxy really is. In photographs taken with modern telescopes, it reveals itself as a sweeping spiral of stunning complexity. The galaxy spans roughly 152,000 light-years in diameter, making it significantly larger than the Milky Way, which stretches across about 100,000 light-years. To travel from one side of Andromeda to the other at the speed of light, the fastest speed possible in the universe, would take over 150,000 years. A commercial airplane flying at cruising speed would need over 100 billion years to make the same trip, roughly 10 times the current age of the universe. These numbers are absurd in their enormity, but they give you some sense of the physical scale of what we are dealing with. Andromeda is home to an estimated 1 trillion stars, roughly 3 times the number found in our galaxy. These stars range from ancient red giants that have burned for over 10 billion years, their hydrogen fuel nearly exhausted, to brilliant blue supergiants that blaze with the intensity of 100,000 suns and will exhaust their fuel and explode as supernovae within just a few million years. Between these extremes are countless ordinary stars like our Sun, unremarkable middle-aged yellow dwarfs that burn steadily for billions of years, potentially hosting planetary systems of their own. The thought that Andromeda could contain billions of Earth-like planets orbiting sun-like stars is both humbling and exhilarating. Though we are still very far from being able to detect individual planets at that distance, Andromeda was long considered to be a classic unbarred spiral galaxy, but infrared observations from the 2-micron all-sky survey and the Spitzer Space Telescope revealed that it is actually a barred spiral. Just like our own Milky Way, a bar is a dense, elongated structure of stars that stretches across the center of the galaxy, channeling gas inward and influencing the dynamics of the surrounding disk. Andromeda's bar is oriented at roughly 55 degrees from the galaxy's major axis, a feature that is difficult to see in visible light because of the galaxy's steep inclination to our line of sight, tilted at about 77 degrees so that we see it almost edge-on. The galaxy also features a prominent ring of star formation located about 32,000 light-years from its center, sometimes called the 10 kiloparsec ring. This ring is a dense concentration of young stars, hydrogen gas, and interstellar dust, a zone of active stellar birth that stands out vividly in infrared and ultraviolet images. The ring's existence is itself a clue to Andromeda's violent past, as simulations suggest it may have been created by the gravitational disturbance of a smaller galaxy plunging through Andromeda's disk, an event we will return to shortly. In 2025, NASA unveiled the largest photomosaic of Andromeda ever assembled, a breathtaking image stitched together from over 600 individual Hubble Space Telescope observations collected over more than a decade. The mosaic captures the glow of 200 million individual stars and spans roughly 2.5 billion pixels. And even this extraordinary image shows only a fraction of Andromeda's total stellar population, because Hubble can only resolve stars that are brighter than our sun. The vast majority of Andromeda's stars, the red dwarfs and dim stellar remnants, remain invisible even to our most powerful telescopes. The structure of Andromeda is rich with detail. Its spiral arms, outlined by glowing clouds of hydrogen gas called H2 regions, wrap around the galaxy like the arms of a pinwheel, dotted with clusters of young, hot stars and dark lanes of interstellar dust. Walter Baade, one of the pioneering astronomers who studied Andromeda in the mid-20th century, described the star-forming regions within the spiral arms as resembling beads on a string, bright knots of stellar birth strung along the curving lanes of the galaxy's disk. At the very center of Andromeda lies a peculiar structure. In 1991, the Hubble Space Telescope revealed that the galaxy's nucleus is not a single bright point of light, but a double nucleus, two distinct concentrations of stars separated by just a few light years. The brighter of the two, designated Pone, is slightly offset from the galaxy's true center. The dimmer one, Pitywo, sits at the exact center of the galaxy and contains a compact cluster of hot blue stars, and lurking within, a supermassive black hole. This black hole, known as M31 star, is a genuine monster. Its mass has been estimated at roughly 100 million times the mass of our Sun, making it roughly 25 times more massive than Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Despite its enormous mass, Andromeda's central black hole is remarkably quiet. It is classified as a low-luminosity active galactic nucleus, meaning it is not currently consuming large amounts of gas or producing the brilliant jets of radiation seen in more active galaxies, but it has not always been so peaceful. In 2023, astronomers using the Hubble and Spitzer space telescopes discovered long filamentary structures of gas and dust spiraling inward toward the black hole, revealing the slow, steady feeding process that keeps it alive, if dormant. And in 2025, analysis of 15 years of data from the Chandra X-ray Observatory revealed that Andromeda's black hole has been flickering, producing brief flares of X-ray radiation in 2006 and 2013 that coincided with bursts of neutrinos detected by the IceCube Neutrino Observatory at the South Pole. These flickers suggest that even a quiet black hole can occasionally stir, offering tantalizing clues about the extreme physics at work near the event horizon of one of the universe's most massive gravitational engines. The double nucleus of Andromeda remains something of a puzzle. One leading explanation is that the brighter clump Pone is not a separate nucleus at all, but rather the densest region of an eccentric disk of stars orbiting the central black hole. The stars in this disk follow highly elongated orbits, lingering at the point farthest from the black hole and creating an apparent concentration of light that looks like a second nucleus. Some astronomers have speculated that this eccentric disk could be the result of a past black hole merger, where the violent release of gravitational waves kicked the stars into their unusual orbits. Whatever its origin, the double nucleus gives Andromeda's heart a unique and enigmatic character. But what we can see of Andromeda, the stars, the gas, the dust, the spiral arms, is only a small fraction of what is actually there. Like all large galaxies, Andromeda is embedded within an enormous halo of dark matter, the mysterious, invisible substance that makes up roughly 85% of all matter in the universe. We cannot see dark matter directly because it does not emit, absorb, or reflect light. But we can detect its presence through its gravitational effects on the visible matter around it. The evidence for Andromeda's dark matter halo comes primarily from the rotation curve of the galaxy. As you move outward from the center of a galaxy, you would expect the orbital velocities of stars to decrease, just as the outer planets of our solar system orbit more slowly than the inner ones. This is what would happen if all of the galaxy's mass were concentrated in its visible stars and gas. But that is not what astronomers observe. Instead, the rotation curve of Andromeda flattens out at large distances, meaning that stars far from the center are orbiting just as fast as those closer in. The only way to explain this is if there is a vast, invisible mass extending far beyond the visible galaxy, a dark matter halo that dominates the galaxy's total mass budget. The virial mass of the Andromeda Galaxy, the total mass, including all dark matter, is estimated at roughly 1 trillion solar masses, comparable to the mass of the Milky Way. Determining which galaxy is actually more massive has been a long-running debate. For decades, Andromeda was assumed to be the heavier of the two, perhaps 25 to 50% more massive than the Milky Way, but more recent measurements, particularly those based on data from the Gaia spacecraft, have revised the Milky Way's mass upward and Andromeda's mass downward, suggesting the two galaxies may be surprisingly similar in total mass. This is an important detail because the mass ratio of merging galaxies significantly affects the outcome of the merger. Two galaxies of roughly equal mass produce a very different result than a large galaxy absorbing a small one. Andromeda's dark matter halo extends far beyond the visible galaxy, stretching out to distances that may overlap with the Milky Way's own halo. Studies using globular clusters and dwarf satellite galaxies as gravitational tracers have suggested that the halo has a prolate shape, meaning it is elongated like a football rather than perfectly spherical. This shape is consistent with predictions from cold dark matter cosmological models, which suggest that dark matter halos form through the hierarchical merging of smaller halos and retain the memory of the directions from which material was accreted along the cosmic web. Andromeda does not exist in isolation. It is the dominant member of our local group, a gravitationally bound collection of galaxies that includes our Milky Way, the Triangulum Galaxy, and roughly 100 smaller galaxies, most of them dwarf galaxies orbiting the two big spirals like moons orbiting planets. The local group spans about 10 million light-years in diameter and has a total mass on the order of 2 trillion solar masses, with the Milky Way and Andromeda together accounting for over 90% of that figure. The term local group was coined by Edwin Hubble himself in his 1936 book, The Realm of the Nebulae, where he described it as a typical small group of nebulae, which is isolated in the general field. At the time, Hubble could identify only about a dozen members. Today, thanks to increasingly sensitive surveys, the count has grown to over 80 known galaxies, with new ultra-faint dwarf satellites being discovered regularly. Most of these tiny galaxies are so dim that they were invisible until just the past few decades. Some contain only a few thousand stars and are so tenuous that they barely qualify as galaxies at all. The structure of the local group has been described as resembling a dumbbell, with Andromeda and its satellites forming one lobe and the Milky Way and its satellites forming the other. The two lobes are separated by roughly 2.5 million light-years and are connected by a gravitational bridge that has been pulling the two galaxies toward each other for billions of years. The gravitational center of the group lies somewhere between the two large spirals, slightly closer to Andromeda, which may be the more massive of the two. Each of the big spirals has its own retinue of satellite galaxies. The Milky Way's entourage includes the large and small Magellanic Clouds, the Sagittarius Dwarf Galaxy, the Canis Major Dwarf Galaxy, and dozens of smaller systems like the Fornax, Sculptor, and Draco Dwarf Galaxies. Andromeda's satellite system is even more extensive. It includes more than 20 known dwarf galaxies, among them Messier 32, a compact elliptical galaxy that orbits close to Andromeda's disk, and Messier 110, a larger and more diffuse dwarf elliptical, NGC 147, and NGC 185 are two additional satellite galaxies that orbit Andromeda as a gravitationally bound pair. But the most intriguing satellite is arguably the Triangulum Galaxy, Messier 33, the third largest member of the local group. Triangulum is about half the size of the Milky Way and contains approximately 40 billion stars, far fewer than either of its larger companions, but still a substantial galaxy in its own right. It is located about 3 million light-years from Earth, slightly farther than Andromeda, and under exceptionally dark and clear skies, it can be glimpsed with the naked eye, making it one of the most distant objects visible without a telescope. The Triangulum Galaxy is a particularly active galaxy. Hubble observations have shown that its rate of star formation is roughly 10 times higher than the average rate in the Andromeda Galaxy. One of its most prominent features is NGC 604, an enormous nebula in one of its spiral arms that ranks among the largest stellar nurseries in the entire local group, spanning nearly 1,500 light-years across and containing over 200 hot young stars that illuminate the surrounding gas with their intense ultraviolet radiation. Triangulum's relationship with Andromeda is complex and somewhat mysterious. The two galaxies are separated by about 750,000 light-years, and observations have revealed a bridge of neutral hydrogen gas connecting them, suggesting they have interacted gravitationally in the past. Some astronomers believe Triangulum may have had a close passage near Andromeda between 2 and 4 billion years ago, an encounter that could have triggered bursts of star formation in both galaxies. Interestingly, unlike the Milky Way and Andromeda, the Triangulum Galaxy does not appear to contain a supermassive black hole at its center, a surprising absence that may be related to the fact that it has no central bulge. The Triangulum Galaxy's future is also uncertain. It may eventually be absorbed by Andromeda, contributing its stars and gas to its larger neighbor. Or it might participate in the eventual Milky Way-Andromeda merger, becoming a third party in the collision. Some simulations show it being flung into a long, looping orbit around the merged galaxy. Others show it being torn apart and consumed. Its fate, like so much else about the future of the local group, depends on details of mass, velocity, and angle that we are still working to pin down. Perhaps the most puzzling aspect of Andromeda's satellite system is the way its dwarf galaxies are arranged. In 2013, astronomers discovered that roughly half of Andromeda's satellite galaxies lie in a thin plane and orbit in the same direction, a configuration that is extremely difficult to explain using standard models of galaxy formation. Under the prevailing cold dark matter cosmological model, satellite galaxies should approach their host galaxy from random directions and orbit on random, uncorrelated paths. The fact that they don't has been a persistent thorn in the side of theorists and has led some to suggest that we may be missing something fundamental about how galaxies and their satellite systems form and evolve. A 2025 study confirmed that this asymmetric distribution is a significant outlier in cosmological simulations, with fewer than 0.5% of simulated Andromeda-like systems showing a similarly lopsided arrangement. The Andromeda Galaxy, for all its present-day beauty, has a violent past. And we know this because the evidence is written in the motions and compositions of its stars. In 2018, astronomers Richard D'Souza of the University of Michigan and Vatican Observatory and Eric Bell of the University of Michigan published a landmark study in the journal Nature Astronomy using large-scale cosmological simulations. They demonstrated that Andromeda's massive, metal-rich stellar halo, the diffuse cloud of stars, extending far beyond the galaxy's visible disk, could only have been created by a single major merger with a large galaxy. This was not a series of small nibbles. It was one enormous collision. The researchers estimated that the galaxy that crashed into Andromeda had a stellar mass of roughly 25 billion solar masses, making it the third largest member of the local group at the time. They called this long-destroyed galaxy M32P because they believed its surviving remnant is the compact satellite galaxy Messier 32, that oddly dense little companion that orbits close to Andromeda's disk. M32 has long puzzled astronomers. It is extraordinarily compact for its size, packed with stars in a way that doesn't fit neatly into any standard category of galaxy. If M32 is indeed the stripped-down core of a once much larger galaxy, a galaxy that lost its outer layers during a violent merger with Andromeda, then many of its unusual properties suddenly make sense. The merger itself played out over billions of years. D'Souza and Bell estimated that the collision began roughly 5 billion years ago, with the final coalescence of the two galaxies' nuclei occurring about 2 billion years ago. The evidence for this timing is woven into Andromeda's star formation history. About 2 billion years ago, roughly a fifth of all the stars currently in Andromeda were born in a sudden, galaxy-wide burst of star formation, the kind of dramatic spike in stellar births that is typically triggered by the compression of gas clouds during a major galactic merger. The collision also left behind the Andromeda giant southern stream, a vast arc of stars extending from the galaxy's disk into the surrounding halo, likely a tidal debris trail created when M32P was torn apart by Andromeda's gravity. This stream, first discovered in the early 2000s by deep imaging surveys, is one of the most prominent stellar structures in any galaxy's halo. It stretches for hundreds of thousands of light years, a glowing ribbon of stars that traces the final orbit of the galaxy that created it. There are also stellar shells, concentric arc-shaped overdensities of stars found on the east and west sides of Andromeda that are consistent with the oscillating debris of a galaxy that plunged repeatedly through Andromeda's disk before being fully absorbed. The collision likely explains a number of Andromeda's other distinctive features as well. The prominent ring of star formation at 10 kiloparsecs from the center, which we discussed earlier, may have been created or enhanced by the gravitational disturbance of M32P passing through the disk. the galaxy's unusually thick stellar disk, 8 times thicker than the Milky Way's thin disk, was likely puffed up by the gravitational violence of the merger. Even Andromeda's large bar structure may have been influenced or triggered by the interaction, and the collision may explain why Andromeda's stellar disk is so thick. At roughly 2,600 light-years in height, it is dramatically thicker than the Milky Way's disk, a puffiness that could have been caused by the gravitational disruption of the merger. When a massive galaxy plunges through the disk of another, the gravitational shocks heat up the stellar orbits, causing stars to oscillate more widely above and below the plane of the disk. Over billions of years, these heated orbits produce a thicker, more bloated disk structure. What is particularly remarkable is that Andromeda's spiral structure survived. Many astronomers had long assumed that a merger of this magnitude, involving a galaxy roughly 1/4 of Andromeda's mass, would destroy a spiral galaxy entirely, transforming it into a featureless elliptical blob. Computer simulations had repeatedly shown that major mergers tend to scramble the orderly rotation of a spiral disk, leaving behind the smooth, structureless mass distribution of an elliptical galaxy. But the evidence tells a different story. Andromeda's disk and bulge were already in place before the merger, and the galaxy managed to maintain its spiral form throughout the collision, albeit with significant changes to its structure. The key, researchers believe, was gas. If the merger involved substantial quantities of gas, the gas could settle back into a flat disk after the violence of the collision, forming new stars in a new spiral pattern and effectively rebuilding the spiral structure from scratch. This finding has important implications for our understanding of galaxy evolution, suggesting that even major mergers do not always spell the end for spiral galaxies. As long as there is enough gas to regenerate the disk. In 2023, further evidence of Andromeda's merger history emerged from the Dark Energy Spectroscopic Instrument, or DAISY, mounted on the Nicholas U. Mayall telescope at Kitt Peak National Observatory. Astronomers used DAISY to measure the individual motions of nearly 7,500 stars in Andromeda's inner halo, and found clear signatures of a mass migration event. Stars that had begun their lives in another galaxy entirely and were absorbed into Andromeda roughly 2 billion years ago. The patterns in their motions matched predictions from merger simulations with striking precision. Our view of Andromeda's merger history is paralleled by what we are learning about our own galaxy's tumultuous past. And what we are learning is that the Milky Way, far from being the serene and orderly galaxy we once imagined, is itself a battered survivor of ancient cosmic violence. The Milky Way may look serene from our vantage point within its disk. When you look up at the night sky and see that river of stars stretching overhead, it seems peaceful, permanent, unchanging. But appearances can be deceiving. The Milky Way, too, bears the scars of ancient galactic collisions. And our understanding of this violent history has been revolutionized by a single spacecraft, the European Space Agency's Gaia mission, launched in 2013 with the goal of creating the most detailed three-dimensional map of the Milky Way ever constructed. Gaia is, in many ways, the most ambitious mapping project in human history. Orbiting the Sun at a point about 1.5 million kilometers from Earth, the spacecraft continuously scans the sky, measuring the positions of stars with a precision equivalent to reading a newspaper headline on the Moon from Earth. Over the course of its mission, Gaia has cataloged the precise positions, distances, and velocities of more than 1.5 billion stars in the Milky Way. It has given astronomers an unprecedented three-dimensional view of our galaxy's structure, revealing features that were completely invisible before. By measuring the precise positions, distances, and motions of over 1.5 billion stars, Gaia has given astronomers an unprecedented view of the galaxy's internal structure. And what they have found, hidden in the seemingly random swirl of stellar orbits, is the forensic evidence of ancient galactic crime scenes. Just as a forensic investigator can reconstruct the events of a crime by studying blood spatter patterns, footprints, and displaced objects, astronomers can reconstruct the history of ancient galaxy mergers by studying the orbits, compositions, and ages of stars that don't quite belong. The most dramatic of these discoveries is the Gaia Sausage Enceladus event. In 2018, multiple teams of astronomers announced that they had found clear evidence of a massive head-on collision between the Milky Way and a dwarf galaxy. Roughly 8 to 10 billion years ago, the dwarf galaxy, estimated to contain roughly 50 billion solar masses of stars, gas, and dark matter, plunged directly into the young Milky Way and was completely torn apart. The team, led by Amina Helmi at the Kaptein Astronomical Institute in the Netherlands, named the destroyed galaxy Gaia Enceladus, after the spacecraft that made the discovery possible, and after Enceladus, a giant from Greek mythology who was said to be buried beneath Mount Etna. The collision was cataclysmic. It puffed up the Milky Way's thin stellar disk, creating the thicker disk structure that we observe today. It dumped vast quantities of stars into the galaxy's halo, where they still orbit on highly elongated, needle-like trajectories. When astronomers plotted the velocities of these halo stars using Gaia data, the resulting shape was so distinctive, a long, narrow sausage in velocity space, that they named the entire event after it. The Gaia Sausage. Vasily Bolokurov of the University of Cambridge, who led one of the discovery teams, described the collision in vivid terms. The dwarf galaxy did not survive the impact, and its wreckage is all around us. The stars from the destroyed galaxy were thrown onto extremely elongated orbits, shooting in and out of the Milky Way's center like needles. At least 8 globular clusters, those ancient dense balls of hundreds of thousands of stars held together by their own gravity, were brought into the Milky Way by this collision and are still orbiting our galaxy today, cosmic souvenirs from a galaxy that no longer exists. Roughly half of all the stars in the Milky Way's stellar halo, the diffuse cloud of ancient stars surrounding the galactic disk, are thought to be former citizens of Gaia Enceladus, now permanent immigrants in our galaxy. The chemical fingerprints of these immigrant stars are one of the most convincing pieces of evidence for the merger. Every galaxy has a distinctive pattern of chemical abundances in its stars, determined by the galaxy's specific history of star formation and stellar death. The pattern is like a chemical fingerprint, unique to each galaxy. When astronomers analyzed the chemical compositions of halo stars identified by Gaia, they found that a large population had chemical fingerprints that were distinctly different from those of stars born in the Milky Way, confirming that they had been born in a separate galaxy. But the story didn't end there. In 2024, a new analysis of Gaia's third data release suggested that some of the stars previously attributed to the ancient Gaia-Sausage-Enceladus merger may actually have come from a much more recent collision. Thomas Donlin of Rensselaer Polytechnic Institute and his colleagues studied the wrinkles in the distribution of stellar motions. Wrinkles that form each time accreted stars swing back and forth through the center of the galaxy. Each oscillation creates a new wrinkle, and by counting and measuring these wrinkles, astronomers can determine when the stars were accreted. Donlin's team determined that a significant population of halo stars must have joined the Milky Way less than 3 billion years ago, far more recently than the 8 to 10 billion year estimate for Gaia-Sausage-Enceladus. They named this more recent event the Virgo radial merger, and its discovery is reshaping our understanding of the Milky Way's recent history. The Milky Way's history is constantly being rewritten, Donlin noted, in no small part thanks to new data from Gaia. The Milky Way is not done absorbing smaller galaxies. Right now, at this very moment, the Sagittarius dwarf galaxy is in the process of being torn apart by the Milky Way's tidal forces, its stars being stripped away and stretched into long streams that wrap around our galaxy like ribbons around a gift. These stellar streams are visible in Gaia data, ghostly trails of stars that trace the orbital path of the disintegrating dwarf galaxy. The Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, are also falling toward us and will likely merge with the Milky Way within the next few billion years. A 2025 study found a virtual certainty that the Large Magellanic Cloud will merge with the Milky Way within the next 2 billion years, an event that will profoundly change our galaxy's structure, particularly affecting the central supermassive black hole and the surrounding galactic halo. This is the way galaxies grow, not through stately, gradual accumulation, but through a relentless series of collisions, mergers, and acts of gravitational cannibalism that play out over billions of years. Every large galaxy in the universe, including Andromeda and our own Milky Way, is a composite object built from the absorbed remains of dozens, perhaps hundreds, of smaller galaxies consumed over cosmic time. Astronomers estimate that the Milky Way has experienced at least 60 such merger events since it first formed. Andromeda has absorbed an estimated 100 to 200 low-mass galaxies over the past 12 billion years. Galaxy mergers are not exceptions. They are the rule. They are how the universe builds its largest structures, one gravitational swallow at a time. And the biggest merger of all may still be ahead, the blue shift of the Andromeda Galaxy's light, first measured by Vesto Slipher in 1912, was the earliest clue that something unusual was happening between our two galaxies in a universe where nearly everything is flying apart due to cosmic expansion, where the vast majority of galaxies are racing away from us at speeds proportional to their distances. Andromeda stands out as a striking exception. It is one of only about 100 known galaxies that are actually moving toward us. Its light is compressed toward shorter, bluer wavelengths, the telltale signature of approach, a celestial neon sign flashing the message, "I am coming closer." The galaxy is approaching the Milky Way at roughly 110 kilometers per second, or about 250,000 miles per hour. That sounds fast, and by everyday human standards, it certainly is. It is fast enough to travel from the Earth to the Moon in just over an hour, or to cross the entire continental United States in about 40 seconds. But on cosmic scales, it is a leisurely pace. At this speed, it would take roughly 4 billion years for Andromeda to close the 2.5 million light-year gap between us. And that is exactly the timescale astronomers originally predicted for the collision. But knowing that Andromeda is approaching us is only half the story. Measuring a galaxy's radial velocity, the speed at which it moves directly toward or away from us, is relatively straightforward. Slipher accomplished it over a century ago using basic spectroscopy. The difficult part, the critical unknown that has driven decades of research, is measuring the galaxy's transverse velocity, the speed at which it is moving sideways across our line of sight. This sideways motion determines the trajectory. If Andromeda is heading almost straight at us, with very little sideways drift, a collision is all but certain. But if it has a significant sideways component to its motion, it could sail past us like a car passing on a highway, never making contact despite coming tantalizingly close. Measuring the sideways, or transverse, motion of a galaxy 2.5 million light-years away is extraordinarily difficult. The apparent motion on the sky is so tiny, just milliarcseconds per year, that it is almost unmeasurable. It took years of patient observation with the Hubble Space Telescope to even attempt it. In 2012, a team led by Roland van der Merel and Tony Sohn at the Space Telescope Science Institute in Baltimore published a detailed analysis of Hubble observations spanning 5 to 7 years by tracking the motions of individual stars in Andromeda with unprecedented precision. They concluded that Andromeda's sideways motion was so small that a head-on collision with the Milky Way in about 4 to 5 billion years was virtually certain. The news made headlines around the world. Our galaxy was on a collision course with Andromeda, and there was nothing anyone could do about it. Computer simulations showed a dramatic sequence of events. In about 3.75 billion years, Andromeda would fill the night sky, its spiral arms stretching across the heavens like a luminous river. The two galaxies would begin their first close passage shortly after, their spiral structures distorted by mutual gravitational forces into sweeping tidal tails of stars and gas. After that initial encounter, the galaxies would swing past each other, slow down, and fall back together for a second pass. Over the next few billion years, the two galaxies would spiral inward, gradually merging into a single, massive structure. By about 7 billion years from now, the merger would be complete. The result was expected to be a giant elliptical galaxy, a huge, rounded blob of stars with no spiral arms, no organized disk, and very little gas for new star formation. Astronomers dubbed this future galaxy Milkomeda, a name coined by Harvard astrophysicist Avi Loeb and his postdoctoral researcher T.J. Cox in a 2007 paper. The Triangulum Galaxy, the third member of the local group, might participate in the collision as well, either being swept up into the merger or being flung into a distant orbit. For over a decade, this was the consensus view. The collision was coming. It was unstoppable. And it was one of the few things about the deep future of the universe that we could predict with reasonable confidence. Then came the study that upended everything. In June of 2025, a team of astronomers led by Till Sawala of the University of Helsinki published a paper in the journal Nature Astronomy that fundamentally changed the conversation about the Milky Way Andromeda collision. The paper was titled simply, "No Certainty of a Milky Way Andromeda Collision." What Sawala and his colleagues did was deceptively straightforward. They took the most recent and most precise observational data available, measurements from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft, combined them with updated estimates of the masses of the major galaxies in the local group, and ran 100,000 computer simulations of the future evolution of the entire system over the next 10 billion years. But unlike previous studies, which had treated the Milky Way and Andromeda as an isolated two-body system, Sawala's team included the gravitational influence of the other significant galaxies in the local group, particularly the Large Magellanic Cloud and the Triangulum Galaxy. The results were startling. The team found that there was only about a 50% chance of the Milky Way and Andromeda colliding within the next 10 billion years. And the probability of a collision happening in the previously predicted timeframe of 4 to 5 billion years dropped to just 2%. In roughly half of the simulations, the two galaxies passed each other at a distance of about 500,000 light years, roughly 5 times the Milky Way's diameter, and then moved into a slow orbital decay rather than a dramatic head-on crash. The key factor was the Large Magellanic Cloud, or LMC. Although the LMC has only about 15% of the Milky Way's mass, its gravitational pull runs perpendicular to the Milky Way Andromeda orbital plane. This sideways tug is enough to alter the Milky Way's trajectory, pulling it slightly away from a direct collision course with Andromeda. Think of it this way. If you are rolling a bowling ball straight toward a group of pins, but someone gives the ball a gentle nudge from the side as it rolls, the ball veers off course and misses the pins entirely. The LMC is that sideways nudge. A relatively small galaxy whose gravitational influence is oriented at just the right angle to potentially deflect the Milky Way away from its date with Andromeda. The Triangulum Galaxy had the opposite effect. Its extra mass pulled the Milky Way slightly more toward Andromeda, but the LMC's influence was stronger. The interplay between these competing gravitational tugs, combined with the inherent uncertainties in the measured velocities and masses of the galaxies involved, is what produces such a wide range of possible outcomes in the simulations. Carlos Frank, a co-author of the study and professor at Durham University in England, summarized the implications with evident wonder. "Until now, we thought this was the fate that awaited our Milky Way galaxy," he said. "We now know that there is a very good chance that we may avoid that scary destiny." The previous consensus that Andromeda and the Milky Way were destined to collide had been based on the best data available at the time, but it did not account for the full complexity of the gravitational environment. The new study considered 22 different variables that could affect the collision, including uncertainties in the positions, velocities, and masses of all the major galaxies involved, and used a statistical technique called Monte Carlo simulation, which explores the full range of possible outcomes by randomly sampling from the distributions of uncertain quantities, even using the latest and most precise observational data available. Sawala said, "The future of the local group is uncertain." Intriguingly, we find an almost equal probability for the widely publicized merger scenario, or conversely, an alternative one where the Milky Way and Andromeda survive unscathed. The study also emphasized an important nuance. Even in the scenarios where the two galaxies don't collide head-on, they don't necessarily escape each other entirely. In roughly half the simulations, the two galaxies make a close flyby, passing within about 500,000 light years of each other, close enough for their gravitational interaction to strip some stars from each other, distort their structures, and potentially trigger some star formation. After this first flyby, the two galaxies would move apart, but dynamical friction, the gradual loss of orbital energy through gravitational interactions with surrounding matter, would slowly bring them back together. Eventually, even in these flyby scenarios, the two galaxies would merge, but on a much longer timescale of 7 to 8 billion years, rather than the previously predicted 4 to 5. Scott Lucchini from Harvard and the Smithsonian Center for Astrophysics praised the study's approach, noting the importance of properly accounting for all the uncertainties. "This really gives us the whole picture of what could happen in the future," he said. The study emphasized that the new conclusions do not mean that previous calculations were wrong. Rather, the earlier work had assumed most likely values for uncertain quantities, whereas the new study explored the full range of possibilities. The result is not that the collision is impossible, but that its certainty has evaporated. However, the story may not be settled yet. In March of 2026, a new numerical study by H. Wu and colleagues, highlighted by Harvard astrophysicist Avi Loeb, used the latest and most precise Gaia-based proper motion measurements for stars in Andromeda, and arrived at a significantly higher merger probability of roughly 90%, with a median merger time of about 6.5 billion years. This study used a different set of proper motion measurements and a different methodology, and its results essentially pushed back toward the earlier consensus, though with a longer timeline than the original 4 to 5 billion year prediction. The disagreement between the two studies highlights just how sensitive the predictions are to small uncertainties in the measured velocity of Andromeda. A difference of just a few tens of kilometers per second in the galaxy's sideways motion can make the difference between a head-on collision and a clean miss. The debate is ongoing, and new data expected from the Gaia telescope in the summer of 2026 should help refine the measurements of Andromeda's transverse motion and narrow the range of possibilities. Until then, the fate of our galaxy remains, fittingly, a cosmic coin toss. What is clear is that our understanding of the Milky Way Andromeda collision has become far more nuanced than the simple, headline-grabbing story of an inevitable cosmic crash. The future of our galaxy is genuinely uncertain, balanced on a knife's edge between collision and survival. But let's imagine, for the sake of exploration, that the merger does happen. What would it actually look like? What would it mean for the stars, the planets, and the vast expanses of space within both galaxies? This is where the science becomes wonderfully counterintuitive, because a galaxy collision is nothing at all like what you might expect. The first thing to understand is that, despite the dramatic language we use, despite words like collision and crash and merger, a galaxy collision is nothing like a car crash. There are no explosions. There are no shattering pieces. No stars slam into other stars. No planets are crushed. The reason is simple. Galaxies are mostly empty space. Overwhelmingly, spectacularly, almost inconceivably empty space, even though Andromeda contains roughly 1 trillion stars, and the Milky Way roughly 300 billion. The distances between individual stars are so vast that the probability of any two stars from the two galaxies actually colliding is almost exactly 0. To put this in perspective, consider the scale. If our sun were the size of a ping-pong ball, the nearest star, Proxima Centauri, would be another small ball located about 1,100 kilometers away. Roughly the distance from New York to Chicago. The average distance between stars within the Milky Way is roughly 100 billion kilometers, or about 1,000 astronomical units. That is like placing one ping-pong ball every 2 miles across a vast, empty landscape. When two galaxies merge, these ping-pong balls pass through each other's space with enormous room to spare. In a detailed mathematical analysis of the problem, the average distance between a star from one galaxy and the nearest star from the other galaxy, even at the moment of maximum overlap, would still be about 1/3 of a light year. That is a gulf of space spanned by roughly 2 million suns lined up end to end with their surfaces touching. The stars would sail past each other with all the nonchalance of ships, passing in opposite directions across a vast and empty ocean. Not a single star would be scratched. But the gravitational effects would be spectacular, visible across millions of light years to any alien astronomer watching from a distant galaxy. As the two galaxies approach each other, long before any physical overlap occurs, their mutual gravitational pull would begin to deform their shapes. Tidal forces, the same kind of forces that cause the moon to raise tides on Earth's oceans, but operating on a scale billions of times larger, would stretch and distort both galaxies. The leading edges of each galaxy would be pulled toward the other, elongating their shapes. Long streamers of stars and gas would be pulled outward, forming sweeping tidal tails that could extend hundreds of thousands of light years into intergalactic space. These tidal tails are a hallmark of interacting galaxies, and we can see them in countless galaxy pairs throughout the observable universe. The Antennae Galaxies, a pair of interacting spirals about 45 million light-years away in the constellation Corvus, are perhaps the most famous example. Their two enormous tidal tails stretching out like the antennae of an insect, earning them their distinctive name. The orderly spiral arms of both the Milky Way and Andromeda would be disrupted and eventually destroyed. The elegant pinwheel structures that define spiral galaxies depend on a delicate balance of gravitational forces, rotational dynamics, and density waves that propagate through the galactic disk. The gravitational perturbations of a major merger would shatter this balance, scrambling the stars into chaotic orbits and erasing the spiral pattern entirely. In NASA simulations of the merger, the sequence of events unfolds over billions of years. At about 2 billion years from now, Andromeda would be visibly closer in the sky, growing brighter and larger as it approached. Its disk, currently seen as a narrow band due to its steep inclination, would gradually fill more and more of the sky. At 3.75 billion years, Andromeda's disk would fill the night sky, its spiral arms stretching across the heavens, and the first gravitational distortions would become apparent. Stars would begin to shift from their familiar positions as the gravitational field of the approaching galaxy began to compete with the Milky Way's own gravity. In about 4 billion years, the two galaxies would make their first close passage. This first encounter would be dramatic, but not final. The Milky Way's disk would be warped and stretched, and Andromeda would be similarly distorted. The sky would brighten dramatically with the light of newly formed stars, as the compression of giant molecular gas clouds triggered a burst of star formation, which astronomers call a starburst event. Giant clouds of hydrogen gas from both galaxies, normally drifting in relative stability, would slam into each other at high speeds. The resulting shockwaves would compress the gas to densities sufficient to trigger gravitational collapse, sparking the formation of millions of new stars in a cosmic fireworks display. Many of these newly born stars would be massive, burning through their nuclear fuel in just a few million years before detonating as supernovae, scattering heavy elements across the merged galaxy and filling space with expanding shells of hot gas. After the first pass, the galaxies would swing past each other, carried by their momentum, but gravitational drag, a process physicists call dynamical friction, would slow them down. The two galaxies would separate, reach their maximum distance, and then fall back together for a second encounter. With each successive pass, more orbital energy would be dissipated, pulling the galaxies closer and closer together. The process is a bit like two dancers who start far apart, swing past each other, slow down, turn around, and come together again. Each time a little closer, each time a little more intertwined, until finally they are one. Around 5 billion years from now, the cores of the two galaxies would appear as a pair of bright lobes in the sky. Two dense concentrations of old stars surrounded by a swirling chaos of disrupted stellar orbits and glowing gas. Star-forming nebulae would be less prominent by this point, because the most intense phase of the starburst would have consumed much of the available gas. And by about 7 billion years from now, the two galaxies would have fully merged into a single, massive, elliptical galaxy. And then there are the black holes. This is where the merger story takes its most dramatic turn. Both the Milky Way and Andromeda harbor supermassive black holes at their centers. These are not ordinary black holes, the kind that form when a massive star collapses at the end of its life. These are monsters of an entirely different order, containing masses equivalent to millions or billions of suns, compressed into regions smaller than our solar system. Sagittarius A star, the Milky Way's black hole, has a mass of roughly 4 million solar masses. It was first detected through the extraordinary orbits of stars near the galactic center. Stars that whip around an invisible point at velocities of thousands of kilometers per second, tracing out orbits that could only be explained by an enormous concentration of invisible mass. The 2020 Nobel Prize in Physics was awarded in part for this discovery. Andromeda's central black hole, M31 star, is far larger, at roughly 100 million solar masses, roughly 25 times more massive than our own galaxy's central black hole. During the merger, these two black holes would not collide immediately. The merger of the galaxies themselves would take billions of years. And even after the two stellar systems had fully interpenetrated and begun to settle into a single structure, the two black holes would still be separated by enormous distances. They would gradually spiral toward each other, drawn together by dynamical friction. As each black hole moved through the combined sea of stars, gravitational interactions would transfer energy from the black holes to the surrounding stars. Each close encounter with a star would give the star a tiny gravitational kick, sending it flying outward on a higher energy orbit, while the black hole lost a corresponding amount of orbital energy and sank a little deeper toward the center over millions of years. This process, sometimes called the gravitational slingshot, would slowly but inexorably draw the two black holes together. When the two black holes came within about 1 light year of each other, the process would accelerate dramatically. At this distance, they would begin to emit powerful gravitational waves, ripples in the fabric of space-time, predicted by Einstein's general theory of relativity, and first directly detected by the LIGO observatory in 2015. These gravitational waves would carry away orbital energy far more efficiently than dynamical friction, causing the black holes to spiral inward faster and faster. The final inspiral and merger would happen in a matter of hours, as the two black holes whirled around each other at a significant fraction of the speed of light, before finally combining into a single, even more massive black hole. The gravitational wave signal from this merger would be detectable across the entire observable universe, a cosmic announcement that two galaxies had become one. The merged black hole, now containing over 100 million solar masses, could become temporarily active if gas from the merger fell into its gravitational pull. This could create a quasar, or an active galactic nucleus, an intensely luminous beacon of radiation, powered by matter spiraling into the black hole at nearly the speed of light. Heated to temperatures of millions of degrees, such an event could release as much energy as 100 million supernovae, briefly making the center of the merged galaxy one of the brightest objects in the visible universe. This blaze of activity would eventually subside as the available fuel was consumed, and the black hole would settle into a quiet dormancy, sitting silently at the heart of the newly formed elliptical galaxy. The effects on our own solar system would depend heavily on where we ended up. Based on simulations from 2007, there is about a 50% chance that the solar system would be swept out to roughly 3 times its current distance from the galactic center, landing far out in the merged galaxy's halo. There is also about a 12% chance that the solar system could be ejected from the merged galaxy entirely, flung out into intergalactic space as a rogue star system, drifting alone through the cosmic void. In either case, the sun and its planets would likely survive the merger intact. The gravitational forces involved operate on galactic scales, too diffuse to directly affect the orbits of planets around individual stars. But here is the important caveat that puts all of this into perspective. By the time any merger might occur, the Earth will already be uninhabitable. Our Sun is currently about 4.5 billion years old, roughly halfway through its roughly 10 billion year lifespan. In about 1 billion years, the Sun's luminosity will have increased enough to trigger a runaway greenhouse effect on Earth, boiling away the oceans and making the surface too hot for liquid water. In about 5 billion years, the Sun will swell into a red giant, expanding to engulf Mercury and Venus, and possibly Earth as well. As Tilsawala noted in 2025, the short answer is that the end of the Sun is far worse for our planet than the collision with Andromeda. The galaxy may or may not survive. Earth certainly will not. If the merger does occur, the resulting galaxy, Milkomeda, would be unlike either of its parent galaxies. Gone would be the graceful spiral arms that define both the Milky Way and Andromeda today. In their place would be a massive elliptical galaxy, a smooth, rounded structure dominated by old, red stars. Simulations suggest that Milkomeda would contain roughly twice the stellar mass and twice the dark matter of the current Milky Way, a genuinely enormous galaxy, but one with a center showing less stellar density than typical elliptical galaxies. It is also possible, depending on the amount of gas remaining in both galaxies at the time of the merger, that the result could be something other than a pure elliptical. Some models suggest a large lenticular galaxy, a disc-shaped structure without distinct spiral arms, or even a superspiral could emerge. The outcome depends on details we cannot yet predict with certainty. If significant amounts of gas survive the initial starburst, they could resettle into a new disk, creating a galaxy that has the smooth, rounded bulge of an elliptical, but the flat disk structure of a spiral. This kind of hybrid galaxy is called a lenticular galaxy, and examples of them are common in the nearby universe, often found in the aftermath of relatively gentle mergers. What would the night sky look like from within Milkomeda? That depends entirely on where our solar system ends up. If we are swept into the outer halo, the sky would be dramatically different from what we see today. Instead of the brilliant band of the Milky Way stretching across the heavens, we would see a diffuse glow of old, red stars spread unevenly across the sky. The central bulge of Milkomeda glowing like a vast, hazy lantern. There would be no spiral arms to mark out the plane of the galaxy. The constellations we know today would be completely unrecognizable. Their component stars flung into new orbits by the gravitational chaos of the merger. Entirely new patterns would emerge, but there would be no humans left to name them. If we are instead ejected from the galaxy entirely, the view would be even more remarkable. Our solar system would drift through intergalactic space, surrounded by an almost perfect darkness. Milkomeda would appear as a distant, fuzzy blob, a galaxy seen from the outside, shrinking slowly as we receded from it. There would be no nearby stars, no Milky Way band, just an isolated solar system drifting in a void of black emptiness, a tiny island of light in an ocean of nothing. Over the next 150 billion years, the remaining galaxies of the local group, including whatever remains of the Triangulum Galaxy, the large and small Magellanic Clouds, and the dozens of dwarf galaxies orbiting the merged system, would gradually be absorbed as well. Their stars and gas folded into the growing bulk of Milkomeda. Eventually, the entire local group would consist of a single enormous galaxy, a quiet monument to the gravitational forces that had, over tens of billions of years, drawn everything together. But beyond that merged galaxy, the universe would continue expanding. Dark energy, the mysterious force accelerating the expansion of the cosmos, would push all other galaxy groups and clusters farther and farther away. The light from distant galaxies, already stretched by the expansion of space into longer and redder wavelengths, would eventually be stretched beyond the limits of detection. Galaxies that are visible to us today would fade from view, one by one, as they crossed the cosmic horizon, the distance beyond which light can no longer reach us, because the space between us is expanding faster than the speed of light. Eventually, trillions of years from now, Milkomeda would be utterly alone, the only galaxy visible in an otherwise empty sky. The cosmic microwave background radiation, the faint afterglow of the Big Bang that currently permeates all of space, would be redshifted to undetectable wavelengths. An astronomer born in that distant era, studying the sky with instruments as powerful as our own, would see nothing beyond their own galaxy. They would have no evidence that other galaxies exist or ever existed. They would have no evidence that the universe is expanding. They would have no reason to suspect the Big Bang. The entire history of cosmology, the great intellectual achievement of the 20th and 21st centuries, would be invisible to them, erased by the expansion of space itself. They would look out at a dark, empty sky and conclude, quite reasonably, that their galaxy was alone, that it was everything, that there was nothing else. This is the ultimate fate that awaits all gravitationally bound structures in the universe. The expansion of space will eventually separate all galaxy clusters from each other, leaving each one isolated in an endlessly growing ocean of emptiness. Within those islands, the last stars will burn through their fuel and die, one by one, until the universe is left with nothing but cooling stellar remnants, slowly evaporating black holes, and the faint, fading glow of a cosmos winding down to its final equilibrium. But that is so far in the future that it borders on the purely theoretical. Right now, in this moment, the Andromeda Galaxy is a source of wonder, not dread. It is a laboratory for understanding how galaxies work, how they form, how they merge, and how they evolve. Because we are embedded inside the Milky Way, we cannot see our own galaxy's structure clearly. We are, as astronomers have said, like someone trying to understand the layout of a city while standing in the middle of its central park. Andromeda is our mirror. It shows us what a spiral galaxy looks like from the outside, and by studying its stars, its dust, its gas, its history of mergers and collisions, we learn about ourselves. This is why the 2025 Hubble mosaic of Andromeda is so much more than a pretty picture. By mapping the ages, compositions, and positions of 200 million individual stars across Andromeda's disk, astronomers can reconstruct the galaxy's entire life history. They can identify populations of stars that were born in different eras, trace the patterns of star formation that were triggered by past mergers, and compare Andromeda's evolutionary path with our own galaxy's history. What they have found is that despite being cosmological neighbors, growing up in the same gravitational environment, the Milky Way and Andromeda have followed remarkably different evolutionary trajectories. Andromeda appears to have had a much more turbulent recent history, with more active star formation and more violent interactions with other galaxies. One astronomer described Andromeda as looking like a train wreck compared to the relatively orderly Milky Way, understanding why two galaxies that formed at roughly the same time and in roughly the same environment ended up so different is one of the great open questions in modern astrophysics. It speaks to the fundamental role that chance plays in the evolution of galaxies. The exact timing of a merger, the angle at which two galaxies approach each other, and the mass ratio of the two systems, these seemingly small details can have enormous consequences for the resulting galaxy structure, star formation history, and future evolution. The universe is not a machine that produces identical outcomes from similar starting conditions. It is a place where contingency matters, where the role of the gravitational dice can send two galaxies down entirely different paths. The relationship between the Milky Way and Andromeda has been unfolding for billions of years. Their dark matter halos, those enormous invisible spheres of exotic matter that extend far beyond the visible boundaries of each galaxy, are already touching, overlapping in the space between the two galaxies. In a very real sense, the interaction between our two galaxies has already begun. It is just happening so slowly, on such vast scales of time and space, that it is invisible to any single human lifetime. We are also learning more every year. The Gaia spacecraft continues to refine its measurements of the three-dimensional positions and motions of stars in the Milky Way, and crucially, in the Andromeda Galaxy itself. New data expected from Gaia in the summer of 2026 should provide more precise measurements of Andromeda's transverse motion, the critical unknown that determines whether the two galaxies will collide head-on, graze each other, or miss entirely. The James Webb Space Telescope is peering deeper into Andromeda's stellar populations than ever before. And the upcoming Nancy Grace Roman Space Telescope, essentially a wide-angle version of Hubble, will be able to capture the equivalent of 100 high-resolution Hubble images in a single exposure, promising to revolutionize our understanding of Andromeda's structure. There is something deeply moving about the idea that two galaxies, each containing hundreds of billions of stars, each harboring uncountable worlds, are drifting toward each other across a gulf of empty space that would take a beam of light 2.5 million years to cross. The forces involved are invisible. The speeds are imperceptible on human timescales. And yet the outcome, whether collision or near miss, will reshape the future of both galaxies in ways we are only beginning to understand. And perhaps that is the most profound thing about the Andromeda Galaxy. It reminds us of our place in the universe. It reminds us that the cosmos is not static, not fixed, not frozen in place. Everything is in motion. Everything is changing. Stars are born and die. Galaxies collide and merge. The universe itself is expanding, accelerating outward into an unknowable future. We are passengers on a small rocky planet orbiting an ordinary star in the outskirts of an ordinary spiral galaxy. And even our galaxy is not permanent. It is a temporary structure, a brief arrangement of matter and energy that will eventually be transformed into something else entirely. The night sky looks permanent. It looks as though the stars have always been where they are and always will be. But that is an illusion created by the brevity of human life. On timescales of millions and billions of years, the sky is a constantly shifting canvas, painted by gravity and time, and the relentless physics of a universe that never stops evolving. The constellations we see tonight are not the constellations our distant ancestors saw, and they are not the constellations our distant descendants will see. Everything moves. Everything changes. The only constant is change itself. The next time you are outside on a clear autumn night, far from the glow of city lights, look toward the northeast. Find the constellation of Andromeda, the chained princess of Greek mythology. Look for the star Mirage, a reddish point of light in the chain of stars that marks the princess's body. And then look just above and to the right of Mirage for the faint, elongated smudge of light that Al-Sufi noticed over 1,000 years ago. That faint smudge, that little cloud, that unremarkable blemish in the fabric of the night sky, is 1 trillion stars. It is a galaxy as vast and complex as our own. It is the most distant object you will ever see with your unaided eyes. And it has been falling toward us, or we toward it, For as long as both galaxies have existed, it is falling toward us. Or maybe it will miss. We may never know for certain. Not in our lifetimes, and not for many lifetimes to come. But it is there. It has always been there. And for as long as humans have looked up at the sky and wondered what lies beyond, it has been waiting to reveal its secrets. That is the Andromeda Galaxy, our closest giant neighbor, our cosmic mirror, our laboratory for understanding how galaxies live and die. And perhaps, billions of years from now, our other half. Thanks so much for watching. If you enjoyed this video, make sure to hit that like button and subscribe so you don't miss our next deep dive into the universe. Drop a comment below and let us know what you think. Would you want to be around to watch two galaxies collide? We'll see you next time.